Okay, so we've done up to heuristic 15, and this is the last one of this particular part. To increase the pressure of a stream, and I've talked about this a number of times, so it shouldn't be unusual for you or surprising to you. To increase the pressure of a stream, pump a liquid rather than compress a gas. That is, condense a vapor as long as refrigeration is not needed before pumping. Because when you've got refrigeration, you've still got compression of a vapor. A refrigeration loop does compress a vapor in any case. So, so that's something that you applied in your tests, that you always want to pump the liquid before you start heating it up, before it goes into the reactor. So the reason for this is work done by pumping or compression is given by work per time, that is kilowatts essentially. The kilowatts is there's the volume flow rate, cubic meters per second, from pressure 1 to pressure 2. So if you've got liquid, then of course the volume flow rate is constant. Then it's easy to do the integration. If you've got a vapor, of course your volume flow rate is getting less and less as you're compressing, as it goes from pressure 1 to pressure 2. So you can apply the appropriate gas law over there, and you'll be able to do that integration. But the big thing is, as a rule of thumb, you can say that vapor has got about 1,000 times more volume than the liquid, than the associated liquid. So essentially, the amount of work to compress a certain mass flow of vapor is going to be 1,000 times more than pumping a liquid across the same pressure difference. So it follows that it is more efficient to pump a liquid than to compress a gas. Thus, it is almost always preferable to condense a vapor, then pump it, and then re-vaporize it, rather than compress it. The other reason, of course, is not only because of this work, which is running costs in a plant. In other words, you have to pay for the electricity if it's an electrical engine. But it is also the capital cost of the equipment, because compressors are much more expensive capital-wise. And you'll see in your design project, when you start doing the capital costing of your plant, you'll find that the biggest cost items in your plant are compressors. So in general, with design, you try and compress once. In other words, you will have the highest pressure at the start of your process, and you will have distillation columns going from the highest pressure down to the lowest pressure, so that you only have to compress once. And preferably there would be a liquid, as in the example I gave you in the test, where the reactants going in are liquids anyway. You will rather pump those liquids, and then you can reduce the pressure as you go through your distillation train. Okay, and yeah, that's pretty much it. Before we go on to the next slides, next set of slides, any questions? Okay, let's fix that. Navigate files. We add share files. Heuristics 2. Yuri, sorry. Speak.
The question is that...
Oh, wait a minute. How's the sound? Because I actually am using the speakers rather than the earbuds. How's the sound been? Would you prefer me to go to speakers? Is that better?
It
Okay,
sounds round about the same.
okay,
Anyways,
all right.
so
Yeah.
at what boiling point would the line be drawn? Because I don't think that natural gas is transported as a liquid um, between plants.
Exactly. That's big. That's why in this slide we've got this thing where it says as long as refrigeration is not needed before pumping. So anything with a boiling point of around 40 or higher, you would condense first. So anything that's liquid at normal room temperature, you would want to condense first, really. Because
Okay,
remember
excellent.
that 40 degrees is what we talked about when you've got cooling water at 30 degrees, 10 degrees C temperature difference for cooling it down. You have 30 degrees C cooling water. If your process stream is 40 degrees, then you've got your 10 degrees C difference to cool it down, and therefore 40 degrees is pretty much a boiling point. The boiling point cutoff, and that's again exactly the same. Your test is a good example there. We took it down to 40 degrees and tried to separate the CO from the normal liquids, and then we could go with the normal liquids and go into a liquid separation, which is much easier, of course. Good. Right. So Heuristics 2 is loaded. Let's go and share now. At first, I've got to unshare this one. Share files. Not this one. This one. Yes. Share now. Okay, so this next section of the heuristics, we're going to do separations that involve solids, heat exchangers and furnaces, pressure changes, and solids handling. Right, so we were on, we missed a 17. I think we missed a 17. Never mind. It might be just my numbering that went wrong. Separate organic chemicals by melt crystallization with cooling using suspension crystallization followed by removal of the crystals by acetylene filtration or centrifugation. So when you've got organic chemicals and you start cooling them, eventually they'll start freezing. And when they freeze, they tend to make pure crystals of the one type. So that's an easy way. Thank you. It looks like I've missed two. Yes, that's why I missed the first one. Thank you very much. Crystallize. Okay. So we're going back to the missing heuristic. Crystallize inorganic chemicals from a concentrated aqueous solution by chilling when solubility decreases significantly with decreasing temperature. So now we're talking inorganic chemicals. Keep the solution at most 1 degree C below the saturation temperature at the prevailing concentration. Okay, now this is, consider that you've got a solution of salt water, of sodium chloride solution, and you cool it down, and you heat it up. You can dissolve more salt in a heated solution. As you cool it down, you're going to get stuff coming out of solution. You will get sugar crystals forming. Now, not sugar crystals. We're talking about salt. You'll have your salt crystals forming, and as you cool it down, you should cool it down slowly, because if you go below the saturation temperature, you have a driving force for the crystals to form, and you want that driving force to be slow so that you make big crystals. So if you cool it down really quickly, you're going to get a lot of very tiny crystals forming. It will just, the solution will go milky white, and you'll have a lot of very, very fine powder crystals, and that will be difficult to separate. So this is why they say keep the solution at most 1 degree C below the saturation temperature at the prevailing concentration. As you're cooling it down, more and more stuff is coming, more and more salt is coming out of solution and forming crystals, and you slowly bring down that temperature until eventually you've saturated out most of the salt in the form of the solid crystals. Use crystallization by evaporation rather than chilling when the solubility does not change significantly with temperature. So here I've used, and I'm going to draw a graph now, so I'm going to start trying to use these tools. These drawing tools, we're going to blue, and I'm going to make some axes right next to this. Whoa, that's not what I wanted to do, but that's fine. I want to go to a line, a real line. There's the axis, and now we talk about. Wait, let me put something on the axes, the labels. So what we've got here is temperature. No, this will be the concentration. And on the x-axis, we have put in temperature. And I'm doing it this way because you want your independent variable to be on the x-axis. So as we change temperature, we are changing the saturation concentration. So as we go down in temperature, the concentration will increase. Saturation. No, the concentration will decrease. Sorry, I need to find a line. Why is this line not drawing? I haven't chosen it. Okay. Right. So most things you'll have a higher concentration at a higher temperature. So what we want to do is to move in this direction down the line. We want to decrease the temperature, and the saturation concentration, the concentration of the salt, sodium chloride in solution, is going to get less as we have a lower temperature, and therefore the stuff comes out. But sodium chloride has got a line that looks something like this. Let's take sugar, that example that I was talking about earlier, and have a look at what its line might look like. And its line, let's get line again. Its line is probably going to look something like that. And so as you change the temperature, you will get a very good crystallization of your sugar. Because the concentration, with a relatively small change in temperature, the concentration varies greatly, the saturation concentration. So at low temperature, you get your sugar coming out of solution. At a high temperature, it doesn't. And with salt, it might have a lower dependence on temperature. So that's what this last bit of the what the last bit of the heuristic says. Use crystallization by evaporation rather than chilling when the solubility does not change significantly with temperature. So here with salt, you would rather evaporate, and that way you'll be able to get. So think of salt pans. You put out your brine solution out on salt pans, and that will evaporate by natural evaporation, and eventually you'll have your salt left on the salt pan to be collected. All right, so that is heuristic 70. Yeah, Philip.
So why will we not go like 5 degrees centigrade or 10 degrees centigrade below the saturation temperature? Won't the crystallization then be faster and more effective?
It'll be faster, but not more effective, because effective is when you make big crystals. If you make small crystals, they're difficult to separate from the liquid. So you want to grow crystals slowly, because then you'll make big crystals. If you take it down very quickly, it will definitely come out of solution, and it'll make very tiny little, many more little tiny crystals, because the driving force is so high. It will make a crystal even if there's not a crystal already, even though there's not a nucleus for it to start crystallizing on, because the driving force is so high. So if the driving force is low, it would prefer the driving force is not high, and therefore it'll prefer to add to an existing crystal, and therefore you'll get bigger crystals.
Okay, that's why we stay about 1 degree Celsius below the saturation temperature.
Exactly.
Okay, thank you very much.
All right. Right, so let's go on to the next one. Separate organic chemicals by melt crystallization with cooling using suspension crystallization, followed by removal of crystals by settling, filtration, or centrifugation. So this is, if it's possible to do this, 2 organic chemicals, and as you cool them, you'll get crystals forming. But those crystals, because they are crystals, they've got a very definite structure. It will tend to be just one of those 2 organic chemicals that make up those crystals. And so when that is possible, you would want to do it. Because the crystals being pure means that you are separating 2 organic chemicals, or an organic chemical, from the other mixture of chemicals. So that might be a useful technique when you are separating pharmaceuticals from a mixture that was derived from a microorganism growth. As you cool it down, you're going to get different crystals forming, and it might be an effective way to separate out very particular compounds, even if they are in very low concentrations. Okay, alternatively, use layer crystallization on a cooled surface with scraping or melting to remove the crystals. If the melt forms a solid solution instead of a eutectic, use repeated melting and freezing steps called fractional melt crystallization. So this is the sort of technique, same sort of technique as distillation. With distillation, you've got different trays where you are repeatedly evaporating and condensing from one tray to the next. And that's what you can do similarly with crystallization. If the crystal is a mixture of the various components, then you can use repeated melting and freezing steps called fractional melt crystallization. So in other words, melting and freezing, where you freeze and you get a layer on the wall. You drain the liquid, you collect you scrape off the solid that's frozen on the wall, and that is a different concentration to the rest of the liquid that you've drained. And then you can just carry on doing that several times, and the more times you do that, the better, the more pure your separation becomes. Yes, Angela.
Prof, how would you know to use crystallization or column distillation? Is this heuristic just saying, like, if you can use crystallization, use it, or does it just depend on?
Yeah, crystallization. Okay, so the advantages and disadvantages. They're putting it as if you would always want to use it, and the reason is to crystallize something, you can get separation without using a great deal of energy. When you do distillation, you always need to have a reflux, and therefore a lot of energy in steam usage. You've got to put in energy to get that separation occurring. I've talked about it before, no, maybe not with this class. If you think of entropy and randomness, and you've got two containers, one contains a gas mixture with only A in it, and the other contains a gas mixture with only B in it. When you open a valve between these two containers, they're going to mix, and nothing much will happen. There won't be any heat formed. The things will mix, but a great deal has happened to the entropy. So you've created a lot of entropy by mixing those two gases, and in order to separate them again, you have to provide that much energy, as in normal energy, steam or whatever, to separate them again, because that entropy formation is wasted energy. It hasn't occurred reversibly. So yeah, separation always involves energy, and the smallest amount of energy you'll use is by melt crystallization, because you can get your separation, and all you have to do is to remove that heat of phase change from solid to liquid, or liquid to solid.
Okay, so this heuristic is just saying, like, if you can use crystallization over column distillation, then do that.
Yep, that's right, if you can. And so it's not always that you're going to get this nice pure crystal forming, but even if you do, sometimes you can do this repeated steps of fractional melt crystallization. So whenever you crystallize, you tend to find that it's going to you need an indirect heat transfer, or a cooled surface, and usually it sticks to that surface, and that's why they call it layer crystallization, and therefore you have to actually scrape. You've got to use mechanical scraping to take it off, or you can add heat in a cyclical sort of way. So in my opinion, this heuristic 18 is more suited when you've got specialty chemicals, like I was talking about in the pharmaceutical industry, because this melt, making a crystal, cooling it down, making a crystal, and then melting it again. You've got repeated heating and cooling cycles, and that's not suitable for a continuous process, a bulk process like we as chemical engineers tend to think of. So I think this is more, these heuristics 17, 18 tend to be more. 17 is still good for large scale, but 18 I would say is more for specialty chemicals. Yeah, exactly. That's a very good point, Peter. That heat can destroy some of the valuable organic chemicals, especially in the pharmaceutical industry. So yeah, that's an important aspect. In fact, yeah. I'm just thinking in brewing, we first use enzymes to convert starch into sugars, and then that sugar solution contains proteins, and then we boil that solution to change the formation of the proteins, the structure of those proteins, and they come out of solution. And then when you cool it down again, so when you boil it and the proteins come out of solution, it's called hot break. And when you cool down that wort again, additional proteins come out as cold break. So some of them come out hot and some of them come out cold. So the point is that when you use boiling like that, you can destroy some of the organic, or organic chemicals, if you wanted them, like in the pharmaceutical industry, you wanted a certain protein and you wanted to separate that out, then you might destroy that by boiling. But if you cool it, you do what in brewing is the cold break. As you cool it, you see the white cloud forming, and that settles out in the fermenter, and that is called cold break, and that is generally related to proteins. And those proteins could be, that process of cooling down and removing the proteins in that way could be well suited to pharmaceutical industry. Right. Using multiple evaporators called effects in series, the latent heat evaporization of water is recovered and reused. With a single evaporator, the ratio of the amount of water evaporated, okay, is typically 0.8. Okay, this needs a whiteboard. So I'm going to go back to share content and a blank whiteboard. Ah, there we have it. Good. And I'm going to put in a rectangle, and oh well, I might as well stick with green, seeing we've got it. Right. So these are what we'll call multiple effect evaporators. And here you've got a solution. Let's go to a different color. We've got a solution coming in. Use a pencil. And there's a liquid level. We've got steam. Let's make that red. And I'll still use the pencil. We've got steam in a heat exchanger over here. And condensate that will come off as water down at the bottom there. Right, so if you put, let's call this text 1 kilogram per second steam. This is your solution that contains, let's call it sugar. We're evaporating liquid to make sugar. So here's a sugar solution. You've just crushed your sugar cane, and you get this sugar solution, and that's what's going in over here. And what you'll do is you'll try and increase you'll try and pump this in. So let me go back to black and draw a pump in there. Okay. So you push up the pressure here to, let's call it 4 bar. Now, you will need steam at, let's just think of this solution here. It's at 4 bar pressure. What temperature is it going to boil at? So just for argument's sake, let's say it boils at 130 degrees C. I'm just going to use a C. That, and then we have, am I still on black? Yes, I'm still on black. And now we have the liquid, the vapor coming off here. And the vapor, no, I'm using the wrong color, so I'm going to delete that. I'm going to use red because that is steam. It's valuable stuff, okay? So we go, firstly, I'm going to do a line going from here to here. And there's a liquid level over here. Right, now I'm going to go to red and draw the steam that comes off this first effect. And we pipe the steam down to here. Oh, you probably can't see until I let go of the mouse button. Like that. So there's 1 kilogram per second of steam, and because we put in enough energy to change that steam from vapor to liquid, we probably are making about the same amount of vapor over here. So it's okay. It's not, there'll be some inefficiencies. You might have to preheat this, but this will go up to 0.8 kilograms per second. I'm going to put it over there, 0.8. And it's at 130 degrees C. So now what we can do is to reduce the pressure. So we put in a valve here. Let me just get the right tool here. We put in a valve over here. Horrible drawing. Don't laugh now. That's a valve, believe it or not. And therefore, the pressure of this thing is no longer at 4 bar anymore. Let's say that we're operating this at 3 bar. I'll get my text tool in and I'll say 3 bar there. And therefore, the boiling point is going to be less than 130 degrees C. So let's call it 120 degrees C. You'll be able to look this up on steam tables, except that the high concentration of sugar in here might may raise the boiling point of the solution, but we'll ignore that for now. As you decrease the pressure, the solution is going to boil at a lower temperature. Now, this 130 degrees C steam is, well, it's at 130 degrees C, and you've got 120 degrees C there, so you've got a temperature difference that you can use to extract the energy out of the steam and make condensate. Oh, wait, I need to show you with a pointer. So here you are. You've got 130 degrees C steam coming out in here. It's condensing, and it's condensing all along this line at 130 degrees C, and eventually you can pull out condensate. And that 130 degrees C provides the driving force for this next unit operation. And we can carry on with like this until we run out of pressure, essentially. So we will go back. We will go back to drawing tools, pencil, color red. We've got steam coming off here. Beautiful arrows. And we go black, and we've got our solution, which is getting stronger. It's getting more and more concentrated. And all the time that you're pulling, you can be, crystals will start coming out because you're evaporating. Go to a line, and we go from there to there. We reduce the pressure again. That's a better valve. And now we might be at 3 bar, at 2 bar in this one. And we might be at 110 degrees C. And of course, this steam that's coming off, pointer, the steam that's coming off this one is at 120 degrees C. This thing is operating at 2 bar, 110 degrees C, so there's a temperature difference that can drive the driving force for the heat exchanger, and you can boil off some of this liquid. And you can see you can go on as long as you like. It's really easy to make that 10 bar and have many different effects. So remember, each one of these things is called an effect, and as we go on, we have these different effects. Just going back to finish off this one. And of course, here we're going to have some we might have several effects after that, and we're going to talk about that in the heuristic now. All right, so that's how we're using 1 kilogram of steam, and here we are evaporating 3 kilograms of water out of this stream. This sugary stream that's coming in here, it's getting evaporating more and more water, and so the flow rate is getting less, and that water is essentially coming out as condensate. So it's going in as liquid. This water that's part of the sugar solution is coming in as liquid, and it's exiting as liquid over there and over there, and in all of the effects further down from that. And that's why it's so energy efficient. So we've got 1 kilogram of steam, and by the time we have many effects, we are evaporating many more kilograms of water from that solution. Because wherever we have one of these, it's approximately 1. Okay, it's 0.8, and this one might be 0.64. So you do get a decreasing amount as you go down. In fact, I think it's 0.8 and 0.8. That, yeah. Oh, wait, I haven't got my pointer again. This one is 0.8, and this one is 0.8 kilograms per second. So using many stages essentially shifts the energy. Oh, it's gone. Shifts the energy input from using lots of steam to using less steam, but with the addition of a pump. Well, you'll always have the pump, or you will, or you might start. That cost is nothing. I think the cost is there's not much difficulty about it, except that you need to go to higher pressures. And we'll also talk about what happens with that rise in boiling point. As you get a higher rise in boiling point over here, then it becomes less effective, or you can't have as many things in series before you run out of pressure, or before you run out of pressure, and therefore you can't have as many effects. So Angela, we're going to go and do that now. I'm going to go back to sharing our presentation, share files, heuristic 2, and we are on heuristic 19. Okay, so using multiple evaporators called effects in series. This is where a blackboard is nice, because then I could still have that whiteboard next to this one. The latent heat of evaporation is recovered and reused. That's what they mean by this, is that we were using the steam that we evaporated from the sugar solution as the heating for the next one. With a single evaporator, you can expect to evaporate about 0.8 compared to the amount of steam you're using. So if there's 1 kilogram of steam, you'll have 0.8 kilograms of liquid evaporated. For 2 effects, the ratio becomes 1.6. So it's 0.8 plus 0.8, 1.6, and for 3 effects, 2.4. So remember, I was talking about all of those arrows going down, the condensate arrows that went down. The first one is 0.8, and then the next one is also 0.8, and the next one is also 0.8. And when you add up all those 0.8s, it says that for every 1 kilogram of steam, you can evaporate that much. With one effect, you can evaporate 0.8. With two effects, you've got two condensate streams, both of them 0.8, so you can evaporate 1.6 with 1 kilogram of steam. Three effects, you can evaporate 2.4, and so forth. The magnitude of the boiling point elevation caused by the dissolved inorganic compounds is a controlling factor in selecting the optimal number of effects. The elevation is often in the range of 2 to 5 degrees C between solution and pure water boiling points. When the boiling point rise is small, and 2 to 5 is fairly small, the minimum evaporation cost is obtained with 8 to 10 effects. When the boiling point rise is appreciable, the number of effects is small, because you run out of pressure quite quickly, because the boiling point is rising as you go along from one effect to the next. And there you'll use 6 or less. If necessary, boost interstage steam pressures with steam jet or mechanical compressors. I think I better go back to that. Remember, I was talking about running out of pressure. If you boost interstage steam pressures with steam jet, we're going to talk about steam jet compressors when we deal with vacuum systems. So we'll discuss that at a later stage. But using these steam jet or mechanical compressors in between, you don't run out of pressure anymore, and so that can still be an effective, even though you're compressing a vapor, it can still be effective cost-wise to just increase those pressures a little bit, that you can keep. You can still have many of these many of these stages on your multiple evaporators. And here we call using multiple evaporators. The name is commonly called multiple effect evaporators. So the effects but just jumps in between these two words. Multiple effect evaporators is the common way of talking about these things. Okay. Oh, look, we are running out of time. So let's open up for questions. This was an important heuristic. You'll see as you go through some of those examples. Let's go back. This one is an important heuristic. If you go back into some of the exam papers, I'm expecting you to recognize that you should use multiple effect evaporators to increase the sugar concentration in a fermentation system. All right, any questions? You can see now, especially since you've written your test, how I'm expecting you to apply heuristics. So you will not know, you will not have an idea which heuristic to apply until you see, oh, I've got to compress a liquid here. Then you realize that which heuristic you've got to use. I've got to increase the sugar concentration in this stream that's coming out of my fermenter. How do I do that? I will use multiple effect evaporators. So it's important that you know these heuristics essentially off by heart, so that when you see a situation where one of those heuristics, you've got a library of heuristics in your head. You can say, oh, this is where I should be applying this heuristic, and then you go ahead. The other heuristic that we used was heuristic number 10, where we said when you've got a mixture, you cool it down to 40 degrees C, and then you can apply vapor separation on the vapor side, and the liquid stream you can apply liquid separation, which is usually normal distillation. So still no comments. So I guess you're all pretty with it on these heuristics we've gone through today. Okay, there we go. Jacobus. I wonder how do you? First of all, how do you shorten your name? Do you call yourself Jaco or speak to me? Ah, there he is. Oh wow. Oh, that's the M. Okay. Michi. I was reading in English. Miggy. So you didn't have his question, Jacobus, Michael. Oh, there we go. For heuristic 19, why for two effects is the ratio not 0.8? Yes. Okay. So the first, I'm going to see if I can recover that whiteboard with all its markings. Share blank whiteboard. Well, let's just see if it's still blank. Oh, it's blank. Okay. The very first one, we might have to heat up that liquid with sensible heating. And this is the way I always think of it. So the first one, we won't get 1 kilogram of steam for 1 kilogram of evaporation for 1 kilogram of steam, because there might be heating up of the incoming stream. But once you go to the next stream, everything is heated up, and in fact, there is your temperature. You actually gain from the sensible heating, because you're going from a hot. The stream is hotter than the next effect that it's going to, so you actually can get a little bit more than 100% efficiency of steam versus evaporated water. That makes sense to you, Michael? Yes, that's my assumption, because it's the only thing that makes sense to me, that it's the sensible heat. All right, guys. Wait, 2 more comments, huh? Oops, where am I? Yes, I am in chat. Okay. I'm going to stop the recording, and I'll see you tomorrow.